All right, week 5. Week 5? Yes, week 5, asynchronous lecture. You guys, we're getting so close to the end. All right, so yesterday in class, we talked about 4.2. We defined absolute extrema, local extrema, relative extrema. We talked about the difference. We talked about critical numbers. We used critical numbers to figure out absolute extrema on a closed interval. Today, we're going to talk about the mean value theorem, and then we're going to use critical numbers a little bit more today. And we're going to use the mean value theorem. I find it interesting that this whole thing is called the mean value theorem because so much of it is really about looking at intervals on which a function is increasing or decreasing. So we're going to be doing a little bit of that today. And then on Monday, when we get into 4.4, we're going to be talking a little bit about how that relates to finding actual places on your graph where you have minimum and maximum values using your critical numbers. So lots going on in this chapter. We will start here, though, at 4.3, the mean value theorem. All right. So the mean value theorem is sort of the basis for everything that we're going to be doing today. We're going to start out with Rolle's theorem. This is a little bit of a specialized theorem that we're going to use today. We're going to find special conditions on which it applies, and we can use it. Let f be a function defined on a closed interval from a to b. Function defined on a closed interval from a to b. Okay, now, here are your conditions. I'm going to give you 1, 2, 3 of them. And if I ask you on a test to show me whether or not Rolle's theorem can be used, you're going to need to show these 3 conditions and then use the theorem. I know sometimes when we write down theorems, we tend to overlook conditions. This is extremely important because you can't use the theorem if these conditions are not met. The first one is that f is continuous on the closed interval from a to b. Okay. You're going to find that that's going to be a condition for a lot of the theorems that you're going to be looking at in chapter 4. It must also be the case that f is differentiable on the open interval from a to b. So does the derivative exist on that interval? And then the third condition is going to be one of the easiest ones to check. Well, I guess technically continuity can be very easy to check. But the third condition is that f of a, so the function value at the left endpoint, must be the same as the function value at the right endpoint. So whatever's happening in between the endpoints, it could be any number of things, an infinite number of possibilities. What you need to happen is that you need to have the y values be the same at a and b. That's what that means. So let f be a function defined on the closed interval from a to b. If these 3 conditions are met, then there is at least one number c in the open interval for which f prime of c equals 0. Then there is at least one number c in which, in AB, sorry. There is at least one number c in the open interval from a to b for which f prime of c is equal to 0. So Rolle's theorem is guaranteeing us a value in this open interval such that f prime at that value is 0, meaning that the slope of the tangent line at that point is going to be 0 as long as these conditions are met. So I'm going to show you how to use this. First, we're going to verify the conditions. So I'm going to show you how to go through that, and then we'll talk about actually using the theorem. So example 1, verify the conditions of the theorem. So we're going to verify that these conditions are met, and then we're going to find all values of c that satisfy the theorem. Your function is f of x equals x to the 6th minus 3x squared, and we're looking at this on the closed interval from -2 to 2. Okay, so let's look at these conditions. The first one is that your function is continuous on the interval, in our case, from -2 to 2. So we're asking ourselves, f is continuous on the interval. Well, look at it. You tell me. I'll tell you, because technically you can't tell me because you're asynchronous. This is a polynomial function. A polynomial function is continuous for all real numbers. So yes, it is continuous because it's a polynomial. We don't have to worry about any variables in the denominator that are causing us to have any sort of breaks in the graph, like a vertical asymptote creating some sort of discontinuity, or even a removable discontinuity we don't have to worry about in this case. You don't have any radicals that might be causing your expression to not exist for certain values. So this one's good. F is differentiable on the open interval. Well, again, this is a polynomial function. You can't find any place, any value for which the derivative does not exist. The derivative is also going to be a polynomial. Therefore, you can take the derivative and evaluate it anywhere you would like. So F is differentiable on the open interval. Yes, and again, because it's a polynomial. And then the last condition is that we need f of the left endpoint to equal f of the right endpoint. And we're going to verify that just by getting some values together. You can put this in your calculator. But basically, I'm looking for -2 to the 6th minus 3 times -2 squared. Is that equal to 2 to the 6th minus 3 times 2 squared? And then you're going to gauge that. But look at your exponents. -2 to the 6th, +2 to the 6th. These are even exponents, so these quantities are both going to end up being the same. And again, with -2 squared, +2 squared, those quantities are going to be the same. So they will be the same. Make sure that when you enter these in your calculator, you're using parentheses. If you just do -2 to the 6th, remember this is going to take 2 to the 6th and then just apply a negative, and you're not going to get the correct answer. So make sure that when you enter this, you're actually saying -2 to the 6th power minus 3 times -2. Oh, I always do that. That's one thing that drives me crazy about this calculator. Minus 3 times -2 to the 2nd power. Okay. And then you're going to get 52. And then you can do the same thing on the other side, 2 to the 6th minus 3 times 2 squared. And you'll also get 52. You could do that by hand also. 52 equals 52. Yes. All of the conditions for this theorem are met. Therefore, it must be the case that there's at least one number c in this open interval for which f prime of c is equal to 0. So there's somewhere in here where we might have a max or min. There's somewhere in here where we definitely will have a situation where we have a horizontal tangent line to the graph. We just need to figure out where that place is, and it might be more than one place. So in order to figure this out, we're going to take the derivative and we're going to set it equal to 0. So we're going to take f prime of x, which is 6x to the 5th, minus 6x. We're going to set it equal to 0. And then you're going to factor out a 6x, and that's going to leave you with x to the 4th minus 1 equals 0. Remember yesterday I made mention of the fact that we should always solve these by factoring. Now, you know what? I'm going to pop up a little bit further over here. I'm running out of my space here. So we're going to do x squared plus 1, x squared minus 1, because this is actually the difference of two squares. X to the 4th is x squared squared, and 1 is 1 squared. Notice now that you can factor this one more time. I can't factor the sum of two squares, but I can factor x squared minus 1 as x plus 1 times x minus 1. And now I can solve this equation using the zero factor property. And I have 4 different equations that result. And I get x equals 0. This one, x squared equals -1. You can't use that. X equals -1 and x equals +1. So we actually have 3 places in our interval from -2 to 2. One of them is 0, one of them is -1, and the other is +1. We have 3 places where we would look at this and see that we have a horizontal tangent line. So, you know, I have a little graph here in my notes, and I just want to check because I kind of want to point something out if I see it on this graph. If you graph this function, x to the 6th minus 3x squared, I'm going to zoom 6 to zoom standard. See what we get. No. Yeah, this wasn't what I was trying to illustrate, but that's okay. One thing that you will notice is that when x equals 1, or I'm sorry, 1, -1, and 0, you have these minimum and maximum values, local mins and maxes. So that's sort of a graphical representation of what we just showed in this example. So we showed the conditions were met, and then we used the theorem, but the theorem guaranteed that we had at least one place in our closed interval for which we had that horizontal tangent line. Okay, so there's that. Now I want to give you some examples for when Rolle's theorem fails. So this will be example 2. Show why Rolle's theorem cannot be applied. And I think it's really good for us to just get used to looking at these conditions and sort of recognizing what they mean very quickly. So the first function is 3x plus 7 divided by x minus 2, and we'll look at this on the closed interval from 0 to 3. If there's something that jumps out at you right away, call it out first. So you have 3 conditions. You don't necessarily have to start with one versus another. In this case, one thing that's jumping out to me is that I'm clearly going to have a continuity problem, and the continuity problem is going to occur at x equals 2. So if x equals 2, f of x has a vertical asymptote, which is a discontinuity. Now, a discontinuity is not always bad. It just depends on where it is. What we're looking for is that on our interval, we have to have the function be continuous, differentiable, and f of a equals f of b. Now, if I were you, I wouldn't even try f of a equals f of b at this point. You don't need to, because we've already just shown that at x equals 2, the function's not continuous. And that matters in this case because 2 is in our closed interval from 0 to 3. So it's not continuous at 2. It's not going to be differentiable at 2 either in that case. If you take the derivative, I mean, think about what would happen here with the quotient rule. In your derivative, you would have in the denominator the quantity x minus 2 squared. So again, you wouldn't be able to take the derivative at x equals 2. So we could say that one of the conditions that's violated is that f is not continuous on 0 to 3. And you could also say that f is not differentiable. Let's abbreviate that. On 0 to 3. And then we could say this is because f prime of x equals, and who cares what's in the numerator, but we know that the denominator is going to be, I'm just going to write a law. Doesn't matter. The denominator is going to be x minus 2 quantity squared. And at 2, you're going to violate that. You cannot find f prime of 2. So 2 is in the interval, but f is not continuous at 2, and f is not differentiable at 2. So already we violated those conditions. Also, I mean, all you have to show is 1, but if you're asked to list which conditions are violated, well, not only did you violate the first 2, but if you check f of a equals f of b, well, f of 0 is going to be -7/2, and f of 3 is 16. So we could also say that f of 0 is not equal to f of 3. So actually none of the conditions are met in this case. So your homework, I think, will ask you to check off every condition that is violated. So in this particular case for this function, you would check off all of them. I'm zoomed in a little bit more than normal here. I think it's because my camera is a little higher than normal. I just feel like maybe we should be able to see a little bit more on this page. Back up a little bit and see how that goes. Okay. All right, so so that was A. So all 3 conditions were violated for A. For B, let's look at f of x equals 4x squared plus 1 divided by x, and I'm looking at the interval from -4 to -2. And again, right off the bat, you're seeing this variable in the denominator. That's telling you you might have a problem. Not entirely sure. But you could say that f is not continuous at x equals 0, because if the denominator is 0, we can't, we will have a vertical asymptote. So f is not continuous at x equals 0, but 0 is not in the interval from -4 to -2. So we actually don't violate the continuity here. You can't come up with a value between -4 and -2 inclusive, or that will violate the continuity here. So that one's going to be okay. And then note your derivative. If you want to take the derivative, fine, but you don't really have to, because you know that it's going to be in the form such that the denominator is going to be x squared. F prime of x equals blah, blah, blah. Who cares about the numerator? But the denominator is going to be x squared. And again, f prime of 0 does not exist, but 0 is not in our open interval, so we're okay. So we can say check for these, whereas maybe up here, sorry, I should have shown a little bit more of a process. You could have X'd those out, like, nope, nope, nope. These ones are okay. We did not violate the continuity. We did not violate the differentiability. You would be able to take the derivative at any value between -4 and -2. But if you look at f of -4 and ask yourself, is it equal to f of -2? We'll come up with those function values. F of -4 is going to be -65/4, which is not equal to f of -2, which is -17/2. So this is bad. So if you were asked what conditions of the theorem are not met, it would be this one, that f of a does not equal f of b. These first 2 conditions would be fine. So yeah, that's kind of the process that you're going to go through to check these conditions for your theorem. I have one more for you. This one is f of x equals the absolute value of x minus 1. And we're going to look at this on the closed interval from 0 to 2. Okay, now if it helps to graph this, graph it. It's the absolute value of x shifted to the right 1 unit. You can always pop it into your calculator if you must. But looks like this. Remember, your absolute value is that V-shaped graph, the absolute value of x. Well, if you're talking about the positive side, it's x minus 1, which is this leg of the graph. And then if you apply a negative, it's negative x plus 1, which is this way. Okay, so as far as your continuity is concerned, you can graph this entire graph without ever lifting your pencil. You're not dividing by any variables. There's no issue here for continuity. So we would say that f is continuous on its entire domain, so we don't have an issue there. If it's continuous on its entire domain, then it's continuous on the closed interval from 0 to 2. Note, however, that when we start to talk about differentiability, if this is 1, well, 2 is over here. We're going from the interval, we're on this interval from 0 to 2, and you have a sharp point on your graph at 1. Remember that we cannot take a derivative at a sharp point. The derivative will not exist. If you want to show the derivative does not exist, that's fine. You can go through that limit process to show that. It's not necessary, though. All you have to know is that there is a sharp point there, and because there is a sharp point, your function is not differentiable. F is not differentiable at x equals 1 because it has the sharp point. And because 1 is in the interval, we have violated this condition for differentiability. You know, we have to use the open interval here for differentiability. Can't take the derivative at an endpoint. So this condition would not be met. If you wanted to check f of a and f of b, you would actually find that those would be equal. In both cases, you would get 1. So check. So the only condition that's violated here is the differentiability. So you would not be able to apply Rawls' theorem to this particular function on this particular interval. Now, students always want to know, well, what happens if I move the interval over? If all you're doing is avoiding the sharp point, like let's say instead of talking about the interval from 0 to 2, I gave you the interval from 2 to 3, that's fine. You can use Rawls' theorem there because the function will be continuous. Well, actually, you can't use it because then you would violate f of 0 equals, or whatever the endpoints would have to be. They'd have to be the same value. And the only way you're going to get them to be the same y value is if you move over this sharp point. Anywhere over there, they're all going to have the same y value. But that's the only way you're going to get that. So you're not going to be able to guarantee anywhere on this function any sort of horizontal tangent line. So yeah, technically we could talk about a different interval, but then you'd be violating a different condition. You might be continuous, you might be differentiable, but then you wouldn't have the function values being the same. So all things to consider. All right, so let's talk next about the mean value theorem. I don't know why I like this one so much. Don't know. I just do. All right. Let f be defined on the closed interval from a to b. Okay. We don't have as many conditions here. We have just the first two conditions. If f is continuous on the closed interval, and f is differentiable on the open interval, then there is at least one number c in the open interval. Such that, okay, now this is going to be a little different here. This is not your derivative equals 0. All right, so it's going to be f prime of c. So the slope at c is equal to f of b minus f of a all over b minus a. Write that down. And I will tell you what that means because I don't want you to just think this is random. So f of b minus f of a divided by b minus a is the slope of the line from a to b. And a and b are your endpoints. So I want to work through this theorem, and then I want to actually show you this on the graph. We'll look at it and see. Okay. Example 3. We're on example 3. No, I'm going to start on a new page. Last thing I want to do is smash this into the bottom here. Example 3. Verify the conditions of the mean value theorem are met. Usually we just abbreviate this. Then find the numbers c guaranteed by the theorem. Your first example is f of x equals x squared divided by x plus 1. And we're going to look at this on the closed interval from 0 to 1. Okay, we need the function to be continuous and differentiable on our closed interval. Notice that if x equals -1, that's going to be a problem for us because if x is -1, then I'm dividing by 0. Remember that your derivative is going to have the form such that the denominator is x plus 1 quantity squared, and you won't be able to evaluate the derivative at -1 either. So we could say, I just want to put it out there just so that you know, f is not continuous or differentiable at x equals -1, but x equals -1 is not in our interval from 0 to 1. And that would be the only place that would cause you any problems. As long as x is any other value other than -1, your function's going to be continuous, and it's going to be differentiable on that interval from 0 to 1. So we're good to go. We can go ahead and take the derivative, and once we do that, we're going to set it equal to our slope and find that value of c for which those values are the same. So we're going to figure out where the derivative is equal to the slope from a to b. It's kind of up to you the order in which you want to do this. I'm going to find the derivative first, just because it seems like the kind of thing you would normally just kind of jump into. So f prime g minus f g prime all divided by g squared. I saw a couple of you guys on your test cancel out a factor here between terms. Can't do that. Because you would have to be able to factor it out before you cancel it. 2x squared plus 2x minus x squared divided by x plus 1 quantity squared. 2x squared minus x squared is just x squared plus 2x divided by x plus 1 quantity squared. If you want, you can factor out an x, and that will leave you with x plus 2. The denominator stays the same. So there's your derivative. We'll kind of see when we go through what form we want this to go with. But here's our derivative. We're going to set this equal to the slope from 0 to 1. So I'm going to take f of b minus f of a divided by b minus a. So remember that these values are a and b. And by the theorem, I'm taking f of b minus f of a divided by b minus a. So it's just y sub 2 minus y sub 1 divided by x sub 2 minus x sub 1 from algebra. All right, so f of 1 is 1 squared divided by 1 plus 1. F of 0 is 0 squared divided by 0 plus 1. You can do that in your calculator if you don't feel like putting it here. This is 1/2 minus 0 divided by 1, which is 1/2. So this is the slope of the secant line. From 0 to 1. So what we're going to do is we're going to take our derivative and we're going to set it equal to the slope of the secant line, which is 1/2. So we're going to take f prime of x, set it equal to not 0. We're going to set it equal to 1/2. We're going to figure out where our derivative is the same as the slope of the secant line from 0 to 1. In order to do that, I need to get my derivative. You know, I might just go ahead and leave it in this form. I don't know if the factored form is really going to be that helpful. So I'm going to take x squared plus 2x divided by the quantity x plus 1 squared, and I'm going to set it equal to 1/2. And then it's kind of up to you at this point how you want to solve this, but I'm guessing you might want to cross multiply. So that's what I'm going to do. I'm going to multiply crosswise. You guys, everybody knows. For some reason, cross multiplying is one of those things that sticks with students. I don't know what it is about cross multiplying, but I rarely have a student who forgets how to cross multiply. And since we're going to be squaring this quantity anyway, I'm just going to write it out like that so that we can simplify and solve. All right, 2x squared plus 4x equals x squared plus 2x plus 1. Now I need to solve this equation. In order to solve a quadratic equation, I need to get all the terms on one side of the equation, and then if we can factor it, we will. If we can't, we'll just use the quadratic formula. No big deal. But I'm going to go ahead and subtract x squared from both sides. Technically, yeah, you could subtract 2x squared, but I like to have positive lead coefficients if at all possible. I'll subtract 2x from both sides, and I'm even going to subtract 1 from both sides. 2x squared minus x squared is 1x squared. 4x minus 2x is 2x, and then 0 minus 1 is negative 1. So the equation that I'm looking at now is x squared plus 2x minus 1 equals 0. And I'm still trying to solve for x here. And remember that whatever values I find for x, they need to lie inside my interval from 0 to 1. Okay, so you're going to try to do this by factoring first if you can. You're going to look for numbers that multiply to give you negative 1 and add to give you 2. Well, negative 1 and positive 1 don't add to give you 2. And what else are you going to come up with? Nothing. So you're going to have to use the quadratic formula. No big deal. X is negative b plus or minus the square root of b squared minus 4ac all divided by 2a. One thing I like about the asynchronous lecture is that if you are good with the quadratic formula, then you won't need to pause it. But if you're like, holy cow, what just happened? Then you can pause it because it's algebra review that we should be pretty good with by now. But if you need to pause it and kind of regroup and figure out where everything came from, this would be a great time to do it. Negative 2 plus or minus the square root of 4 plus 4. You have a minus and negative, so that's a plus divided by 2. Negative 2 plus or minus the square root of 8 divided by 2. I'm going to simplify the radical. Remember, when you're trying to simplify radicals, you need to figure out their perfect square factors. So I know that 8 has a perfect square factor of 4. So if you split up 8 into 4 times 2, then you can rewrite this as, remember, we can split up the product inside a radical as the product of 2 radicals. Little algebra review here for you in case it's been a while. And then you can simplify the one that had the perfect square factor underneath. And now that you have this 2 in every term, we'll go ahead and factor it out so you can cancel it out. That leaves you with 1 plus or minus the square root of 2 divided by 2. And now you can go ahead and cancel that out. Notice that it was already plus or minus. So when you factor a negative out, it's still going to be plus or minus. You haven't changed anything there. And then you'll get negative 1 plus or minus the square root of 2. Check those approximations so you can verify if they're in your closed interval from 0 to 1. Negative 1 plus the square root of 2 is approximately 0.414. And that is in the interval from 0 to 1. Which would lead you to believe that the other one would not be in the interval. So negative 1 minus the square root of 2 is approximately negative 2.414, not in the interval from 0 to 1. Sorry, running out of space here on my desk. So you have one x value for which the slope of your tangent line at that point would be the same as the slope of the line from A to B. So the answer here would officially be x equals negative 1 plus the square root of 2. If you don't even remember what it was that you were doing here, I'm reminding you now. You were looking for places where, I'll remind you of your theorem actually. We said that if f was continuous and differentiable on these intervals, then there was at least one number c such that f prime of c, that's what we found, is equal to the slope of the line from A to B. Okay. So we found that. If you would like on your own time, you can graph that. It's kind of messy just because In our case, the x value is here. You'd have to find a corresponding y value and to get the actual equation of the line. But you can always just graph the graph and then verify. You can kind of eyeball it and see that the slope at that point looks the same as the slope from A to B. Right. Let's do one more of these. I sometimes think doing these is a really good idea just because it's got a lot of algebra review and it's good for you. Okay. So B, we'll do a radical function. We haven't looked at those today. The square root of x minus 2. We're going to look at this on the closed interval from 2 to 4. Your function is going to be continuous on its domain. The domain of the function, your radical function, is just values such that x minus 2 are greater than or equal to 0. Is greater than or equal to 0. We want this value underneath the radical to be at minimum 0, or any other positive values. So that means that x has to be greater than or equal to 2. So there's your domain. So if we're continuous here, then we'll definitely be continuous there. So that is not going to be a problem for us. And then we're going to look also at the derivative because it's not so straightforward here as far as our differentiability. So we're going to have to look at that. But we can say that f is continuous on 2 to 4. Check. That's positive. F prime, well, remember that we can rewrite f as the quantity x minus 2 to the 1/2 power. So f prime is going to be 1/2 times x minus 2 to the negative half times the derivative of the inside function. I know it's just 1, but I like to show it with the chain rule because I don't want you guys to forget that it exists. You'll get 1 over twice the square root of x minus 2. So this function is not differentiable at 2 because if x equals 2, then we cannot divide by 0 in that case. But let's say not differentiable at x equals 2. Remember, our differentiability is not on the closed interval. Our differentiability is on the open interval. So I would say that x equals 2 is not in the open interval from 2 to 4. So our differentiability actually is good here. We are differentiable inside this open interval from 2 to 4. Remember, this does not include the value 2. It just goes beyond 2, between 2 and 4. So we would say that f is differentiable on the open interval from 2 to 4. Check. So we've shown now that the conditions for the mean value theorem are met. Now we just need to find those values of x such that the derivative is equal to the slope of the secant line from 2 to 4. So we'll do that next. And the nice thing is we already took the derivative, so we don't have to do that anymore. But we can find the slope from 2 to 4. F of b minus f of a all divided by b minus a. F of 4 is the square root of 4 minus 2. F of 2 is the square root of 2 minus 2. So we have the square root of 2 minus 0 divided by 2 is the square root of 2 over 2. So this is your slope from 2 to 4. What we're going to do now is take your slope and set it equal to the derivative so that we can find values such that the derivative or the slope of your on your graph at whatever value x we find is equal to the square root of 2 over 2. So take your derivative and set it equal to the square root of 2 over 2. Okay, now if you're seeing 2's in both of your denominators, those are going to cancel. But if you want, go ahead and cross multiply first. If that wouldn't have been obvious to you, just cross multiply for now and fix it in a minute. So we'll have twice the square root of 2 times the square root of x minus 2. So we cross multiplied. And now you can divide both sides by 2 and say 1 equals the square root of 2 times the square root of x minus 2. Don't say 0, whatever you do. When you divide this out, you still have 1 on the left-hand side. Okay, but we do have to solve for x. And when you're solving radical equations, you need to have the radical isolated. So we're going to have to send this back over as 1 over the square root of 2 equals the square root of x minus 2. So divide both sides by the square root of 2. And then to get the x out of the radical, we're going to square both sides. Now remember, this can cause some extraneous solutions, so we're going to have to check that. But when we square both sides, that's going to allow us to take that variable out of the radical. So you have 1/2 equals x minus 2. And then x is equal to 1/2 plus 2, which is 5x. 2.5 if you want to call it that. It's a terminating decimal, so it's perfectly acceptable. All right, so this is the value at which our graph has a slope such that the slope is the same as the slope of the secant line from 2 to 4. Verify that this is in your interval, by the way. 2.5 is in the interval from 2 to 4. Check. There's your solution, or there's your solution, however you want to think about that. Okay, that was the mean value theorem. Now, I find it interesting that the next thing that I have to tell you is actually a corollary, which is kind of like an afterthought to a theorem, which before I taught out of this book, I never really would have thought about it this way. This is the way it is shown, and that's okay with me. So this is very, very important. This is something that we're going to be doing for the rest of the chapter, talking about increasing and decreasing functions. So increasing decreasing function test. Okay. Let f be differentiable on the open interval from a to b. If f prime of x is greater than 0 on the open interval from a to b, then f is increasing on the interval. I'm going to write the second part of this, and hopefully you're kind of thinking that this relates back to something that we did like last week, which it does, maybe even 2 weeks ago when we were talking about just defining derivatives. We were relating the derivative back to its original graph. And this really just kind of comes from that discussion, which I'll remind you of in a second. If the derivative is less than 0 on A, B, then f is decreasing on the open interval from A to B. All right, so I already mentioned this is incredibly important. It's a result that we're going to be using throughout the rest of the chapter. We're going to be really focusing on finding intervals where your function is increasing or decreasing. And then Monday, when we get into 4.4, we're going to be talking about how that relates back to actually finding those minimum and maximum values. Think about, for instance, if your function is increasing, well, I don't know, it's increasing and then it's decreasing and then it's increasing and doing all of these things. If it goes from increasing to decreasing, it has to have this value somewhere such that it has a horizontal tangent line. But until it gets to that value, the slopes of your tangent lines are all going to be positive. Now, this is just, one little tiny example, but notice that on every point leading up to this horizontal tangent line, all of the slopes of these tangent lines are positive. The lines are all going up from left to right. The closer you get to the top of this hill, the more horizontal they become, but they're still heading up from left to right. The slopes are all positive. This is sort of a visual representation of this corollary that I just gave you. If your slopes are positive, then your function's increasing. But as soon as you get past this point where you hit the top of the hill and you start to descend, well, now you're looking at tangent lines that have decreasing slopes. Sorry, that's not like the best pictorial representation of a tangent line. You'll get to the bottom and you'll hit that vertical tangent line. And then as soon as you move away from that, well, once again, your slopes are positive. So your function's increasing. So I feel like that is pretty intuitive. But basically, if you wanted to think about what this would look like on a graph, that's what it looks like. So we're going to use this now with our discussion of critical numbers from last time. Example 4. Determine intervals where f is increasing or decreasing. So the critical numbers are going to yield these places here at the top and the bottom of your curves. Any sort of local minima or maxima, which will formalize in 4.4. The way your book breaks this down kind of drives me crazy, but just makes more sense to follow the structure as far as your homework is concerned. We're going to find the critical numbers, which are going to give us these values at the top and the bottom. And then in between those values, we need to determine whether your slopes are negative or positive. If they're negative, your curve is going to be decreasing on the interval. If they're positive, your curve will be increasing on the interval. So we're going to be using some test values here to do that. A, f of x equals x squared minus 4x plus 1. You know what? I will actually combine this with the first part of 4.4 because it doesn't make sense to split this up again. I'm going to change it up on the fly. Okay, let's do this part first. And then I'll give you some definitions to go along with the rest of this. All right, f prime of x is 2x minus 4. Remember, to find critical numbers, that's what we're trying to do here. We're trying to find these maximum and minimum values. We set our derivative equal to 0 to find where the slope of the tangent line is 0. So horizontal tangent line. Then we have 2x equals 4 and x equals 2. So x equals 2 is our critical number. Now this time, I'm not giving you, like I did last time, closed intervals on which to check absolute extrema. We're not talking about absolute extrema anymore. That was a 4.2 topic. It's a separate topic. It still uses critical numbers because we still need to talk about what's happening in between the endpoints. But here, we're looking at any place on this graph where we might possibly have a change from increasing to decreasing or vice versa. So what you're going to do is you're going to find that critical number. And then we need to figure out what's happening on both sides of the critical number. Something is happening. I mean, it's a parabola. It opens upward because its lead coefficient's positive. So you're expecting to see this behavior where your function is decreasing and then increasing. There's a change, though, that happens at 2. You need to find what that is and prove this to me using some sort of test value. So we're going to look at values to the left of 2 and to the right of 2. And we're going to show what the slopes of the tangent lines are on each side. If the slopes are negative, which we are expecting on the left of 2, then we'll say that the function is decreasing on that interval. And if the slopes are positive, then we'll say that the function must be increasing on the interval. But something's happening at 2. That's where we either have some maximum or minimum value, which, like I said, I'll define for you in just a minute. All right, so your test, here's what we're going to set up a table. We're going to do this for all of these. We're going to be doing major table work in these next 2 sections. So I'm going to first set up an interval that starts at the first value in the domain. Well, our domain goes all the way down to -infinity, and it goes all the way up to your critical number. And then you're going to have another interval that goes from your critical number all the way up to the rest of your domain. You're going to come up with a test value. Let's say, for instance, 0. Whatever the derivative is at 0, it should be the same value, whether negative or positive, for any value to the left of 2. So you just pick one value that's in that interval, and you shouldn't see any changes elsewhere because the only change happening is right here. If it's negative on the left of 2, it's going to be negative on the whole thing. So you're going to pick a test point. I'm going to go with 0 because it's an easy one to evaluate. And then I'm going to go with 3. 3 is on the interval from 2 to infinity. Then you're going to evaluate f prime at your test value. You're going to try to figure out if your derivative is negative or positive. And then you're going to write down your sign of f prime and tell me if your function is increasing or decreasing on that interval. Okay, so this is where you're using the derivative to evaluate the test point. This one's pretty easy to evaluate. When x equals 0, well, you're going to have 2 times 0 minus 4. I don't even really care what the value is. All I care about is whether it's negative or positive. And 0 minus 4 is indeed negative. Do the same thing for 3. Take your derivative. 2 times 3 minus 4 is 6 minus 4, which is 2. 2 is positive. Okay, fine. Just give me the value. That's fine. If it's going to drive you crazy, kind of drives me crazy not to fill it out. What this means is that any value to the left of 2 is going to have a negative derivative. Now, you showed that with a test point, but you're relying here on your critical number. You're just assuming that the only place where you're going to have a max or min is occurring right here at 2. Anywhere else, it's going to have that same behavior on the left and on the right. So your conclusion would be that f, not f prime, f is decreasing because the derivative is negative on the interval from -infinity to 2, and f is increasing on the interval from 2 to infinity. because your derivatives are going to be positive. Now, I know we only showed that with one test point, but whatever is happening anywhere on the right to the right of 2 is going to be happening at every single value. You can test more if you want, but you'll be wasting your time. As long as your critical number is right, you don't have to worry. Just pick one test value on each side. Okay, I want to finish up example A by bringing in this idea of extrema, because I have A, B, and C. I did a polynomial, a rational, and a trig function. But first, I want to make sure I give you the first derivative test, which is actually from 4.4. And then we won't have to go over it next time and go through these examples again. Last time I did that, it just seemed silly. So this will be better. Okay, so we're going to come back to this. And I'm going to pull all this in with 4.4. I know this is like the only time I'm going to do something so strange like this. You've never seen me do anything strange. Come on. From 4.4, local extrema. We're going to talk about concavity next time, but I'm going to pull in the local extrema piece here. Okay, so we're going to add this to our 4.3 notes. Add this to 4.3 examples. Let's just say that. Okay, so we're going to tie this in with this idea of actually being able to ascertain a minimum or maximum value on the graph. In order to do that, I'm going to give you the first derivative test, which is vital to your life in calculus. It's vital. I'm telling you it is. Here. Theorem. First derivative test. Let f be a function that's continuous on an interval I. Suppose C is the critical number of f. And AB is an open interval in I containing C. Okay. So here are the three things that are going to happen here on each side of your critical number. If f prime of x is greater than 0 for values of x between a and c. Now, a is your left endpoint, c is your critical number, and f prime of x is less than 0 for values of x between c and b. So between your critical number and your right endpoint, I feel like this is actually going to be pretty intuitive. So if you're kind of like, whoa, this is a lot, I can't follow it, you might have an easier time looking at it actually in your table. But this is your official definition. Then f of c is a local maximum value. And I think I'm going to draw you a little graph here so you can visualize this, because it's sort of hard reading off the definition and getting a visual on what's actually happening. So, all right, imagine if your derivatives are positive on the left of your critical number and your derivatives are negative on the right of your critical number, then you have a local maximum. So if your derivatives are positive to the left, and if you want, I don't know. I don't want to close that because it's technically an open interval. A, B. So we're going to have positive derivatives from A to C. So who knows what they're doing? We just know that they're going up. And then negative derivatives from C to B. Should be C. That means that your tangent lines are heading down. Well, the only way for that to happen is if you have a local max at C. So the max is at the top of the hill. Now that works. So your derivatives are positive, meaning the slopes of all the tangent lines are positive, and then your derivatives are negative on the right of C. So that's what that means. And this is the first derivative test. So like I said, we're tying this in with what we just did with intervals for where your function's increasing or decreasing. As long as you know that, okay, my function's increasing over here, decreasing over there, then we can make a conjecture about whether or not your critical number is a minimum or maximum. Or I'm going to give you a case where it's neither. Blow your mind. If f prime of x is less than 0. So this is basically just saying the opposite. Prime of x is greater than 0 for x being between C and B. Then f of C, the function value, is a local minimum value. Okay, so that would be similarly, you have some value C, A, and B. Imagine C is down here. Well, if your derivatives are negative from A to C, that means the slopes of your tangent lines all go down from left to right. If your derivatives are positive from C to B, that means the slopes of your tangent lines go up. Now, it doesn't have to necessarily be, that would make no sense if I did that. They don't necessarily all have to go up and increase in their slopes. I mean, they could sort of start to level out. You could have a curve that looks more like this. But the point is that you should be looking at a situation where C in this case is a local min. So on each side, you've got derivatives having different signs. However, it could be the case that on each side of your critical number, your derivatives have the same sign, in which case we wouldn't be able to make any conclusion about C being a local min or max. We would just say it's neither. If f prime of x has the same sign on both sides of C, then f of C is neither a local max nor a local min. Okay. So that situation, one example of that situation would be we're looking at, A, B, and C, and maybe C's right here. If your derivatives have the same sign on both sides of C, well, remember C is a critical number, so C is the place where you have a horizontal tangent line. But let's say that your slopes have the same sign on both sides. Okay, so maybe they level out for a second as they approach C, but they're positive over here. They're going up from left to right, and then they're also going to be positive over here. In that case, C would be neither a min nor a max. That would look something like this. What that means is that for one split second in time, your graph kind of levels out, but then it continues on with its previous behavior. So C can actually be a critical number and be neither a minimum nor a maximum. And that will sometimes happen. It doesn't happen a lot, but it does happen sometimes. So that's something to keep an eye out for. So the first derivative test is basically just telling us that once we find the critical number, as long as we can show that the derivatives have opposite signs, on each side of the critical number, then we can make a conclusion about whether it's a local min or local max. So if to the left of the critical number, your derivatives are positive and to the right they're negative, well, then you have a local max. If to the left they're negative and to the right they're positive, then you have a local min. That's the first derivative test. Okay. So I'm going to use that now to finish out example 4a, and then we'll also use it on B and C. So I'm going to go back. Sorry, no, this is straight. To example 4a. And I'm going to add something to the instructions here. So determine interval where f is increasing or decreasing. Then determine or I should say, then find any local extrema. Yeah. So we're going to do that part next, now that I've given you that definition. All right. So we found the critical number. I'm going to remind you now where we were. Here was our function for example 4a. We took the derivative. We found the critical number. And then we set up intervals on each side of the critical number to determine what was happening with f prime. Well, we found that the derivatives were negative to the left of our critical number and positive to the right. So we had f decreasing and then increasing. Well, we changed from decreasing to increasing. So if we change from decreasing to increasing, then it must be the case that we have a local minimum at x equals 2. Now, we don't always have, I jotted this down because it was a parabola and we know something about parabolas. But what I normally do here is when we get to the bottom row, the negatives I just send down from left to right. The positives I send up from left to right. And then you kind of can see here this behavior where your function would be going down. And then actually at x equals 2, you bottom out and then you start to go up again. So we can conclude using the first derivative test. X equals 2 yields a local min. And then f of 2 would be the local minimum value. F of 2, go back to your original function. 2 squared is 4, minus 8 is negative 4, plus 1 is negative 3, is the minimum value. So I know it seemed like we just added a ton of information just to make this small conclusion, but we had already done everything else. So that's what these increasing, decreasing extrema problems are going to do. You're going to set up intervals. You're going to determine where your function's increasing or decreasing. And if you change from one to the other, then you need to make your conclusion about what's actually happening with your function at that point. If we went, however, by our test here, if we went from increasing to increasing, then we wouldn't be able to say anything about having a max or a min. We're looking for the behavior to change on each side of the critical number. I'm going to give you B and C, and then we're gonna stop. It's true. B is a rational function. F of x is x squared plus 3 divided by x plus 3. Okay, your instructions were, if I can remind you, determine intervals where your function's increasing or decreasing, and then find any extrema. In order to get intervals where we're increasing or decreasing, we need to find the critical numbers. Remember, when we're looking at a fraction and trying to find critical numbers, we're going to set the numerator and denominator equal to 0, and we're going to make sure that we check to verify that the value is in our domain. So first find the derivative, f prime g minus f g prime all divided by g squared. So let's go ahead and simplify 2x squared plus 6x minus x squared minus 3 in the numerator. And then we have x squared plus 6x minus 3 divided by x plus 3 quantity squared, and that's our derivative. All right. In order to get critical numbers, I need to find places where first of all, where my derivative is equal to 0. So we're going to take our quadratic function and set it equal to 0. And then you're going to ask yourself, are there two numbers that multiply to -3 and add to 6? And unfortunately, you're not going to find them. So you're going to have to use the quadratic formula again, but that's okay. Negative b plus or minus the square root of b squared minus 4ac all divided by 2a. 36 plus 12 is 48. And remember, you're going to split up 48 such that you factor it using a perfect square factor. Technically, you could use 4. However, 4 is not the largest perfect square factor of 48. The largest perfect square factor of 48 is actually 16. You should use the biggest one, otherwise you're going to have to simplify this again. -6 plus or minus the square root of 16 times the square root of 3 divided by 2. 16 times 3 gets you to 48. And I'm doing this so that I can simplify this value. I mean, I guess technically, whether it's simplified or not, you can get an approximation, but I like your answers to be simplified. And you have a common factor of 2 in every term, so you can go ahead and divide by 2 everywhere, or you can factor and cancel that way. 2 divided by 2 is 1. 4 divided by 2 is 2. 6 divided by 2 is 3. And you get -3 plus or minus 2 root 3. We're going to have to come up with test values to the left and right of these two values. So let's go ahead and actually get some approximations here. One of them is going to be the plus variation, and the other will be the minus variation. All right, -3 plus 2 square root 3 is approximately 0.464, and -3 minus 2 root 3 is approximately -6.464. Now, again, you don't have an interval here. You're just looking for any possible places where you have extreme values. We're going to look at these intervals and figure out what's happening to our function as far as whether it's increasing or decreasing on them. And then we are going to, what's we're going to do? Oh yeah, talk about finding extrema, which comes right from that test for increasing or decreasing functions. Okay, so these are two critical numbers. Now, remember that we also have to look for places where the derivative does not exist. Now, technically, the derivative does not exist when the denominator equals 0. So reminding you here, there's your derivative. Take your denominator, set it equal to 0. Well, then you get x cannot be equal to -3. Well, maybe I should say x equals -3 would be a place where our derivative does not exist. However, x equals -3 is not in the domain of f. Looking at your function f, -3 is not in its domain. So we are not going to consider it a critical number. However, think about the fact that there's actually going to be an asymptote at -3. So I'm going to say it's not in the domain of f, so not a critical number. However, there is a vertical asymptote at x equals -3. So it's splitting your graph, and you have to include that in your intervals. You can't just take an interval over that value. It does not work that way because you're probably going to change from increasing to decreasing. I mean, you could change from increasing to decreasing on either side. So we need to include that in our intervals. Do that. So when I set up my intervals, and I'm actually going to do this on the next page just so I don't run out of space. I feel like when I say that, you find it alarming. Don't be alarmed. Sometimes I cannot get this thing to move over. There we go. I have two critical numbers. I have a vertical asymptote. I need to include all of this information in my intervals. Let's go ahead and do that. The domain of my function is all real numbers, not including -3. If you want to note that again up here, domain, all real numbers, not including -3. So if it's not in the domain, we need to include it in our intervals when we set this up to determine whether we're increasing or decreasing on these intervals. That right here, this there. So we're going to go from, let's see, I have the approximate values here, -infinity up to our first critical number, or the asymptote, whichever comes first. But if I'm heading from -infinity to the right, I'm going to hit -6.464 first. So we're going to leave room to label here, test. We're going to go from -infinity up to -3 minus twice the square root of 3. And we'll look at what's happening on this interval. We'll pick a test value. It would be helpful if you put the approximation up here so you have a good idea where you're going to be choosing that test value from. Pick your interval back up again at the critical number and take it up to that asymptote that you have at -3. So we're going to look for a test value in between here. Then you're going to go from your asymptote up to your next critical number, which is -3 plus twice the square root of 3, which is approximately 0.464. And then you're going to go from that value all the way up to the end of your domain, up to +infinity. So the key here is just to remember to include the vertical asymptote in your intervals. You can't just interval over it. I'm going to pick some test values, maybe like -7. That might be a good one to choose because it's in that interval. You'll do that. And then between -3 and -6.464, it's up to you. You decide. I usually try to pick a value that's smaller, so I'm going to go with -4. If you want to pick -3.01, be my guest. Between -3 and 0.464, I'm going to go with 0. If I can use 0, I use 0. It's just easy to evaluate. And then I'll pick 1 for my last interval. I'm going to use these test values. They're going to represent everything that's happening in that interval, and we'll figure out whether or not your function's increasing or decreasing to the left and right of these critical numbers. So we're going to evaluate the derivative at the test point. If you'd like, at this point, there's a lot going on. If I were you, I would probably just put my derivative into my graphing calculator to the table. The derivative was this one. Make sure you enter it using the appropriate grouping symbols. X squared plus 6x minus 3 divided by, open up your parentheses, x plus 3 quantity squared. And you'll be able to evaluate these test values much more quickly if you use your calculator, assuming you entered your function correctly. I'm going to go to my table, and I'm going to look at my test values. -7. Do you need something? Okay. -7. Sorry. -7. -4. 0. And 1. And I'm going to put these values down in my table. At -7, my value is 0.25, so it's positive. At -4, I'm looking at -11. At 0, we have -1/3. And at 1, it is 0.25 or quarter. Now, if you're looking at the exact values, don't be too worried about it. Mostly what we care about is the sign. Yes, I want to see the value because it helps me to know that you actually looked at this in your calculator and didn't just look at the graph and come up with whether your function was increasing or decreasing at that point. I want to know that you know how to do this. But what we're going to look for now is the sign of f prime at your test point. So it's positive, negative, negative, positive. And from there, you can make the conclusion regarding the behavior of your function. So I would say that f is increasing on the interval from -infinity up to your first critical number, and also increasing from your last critical number up to infinity. So f is increasing. You can do lots of abbreviating here on these intervals. And then we'll go up to infinity. And then you can say that f is decreasing on the intervals. Oh, and actually, I'm really glad that we wrote it this way because I wanted to make the point here. Sometimes students will notice that the sign didn't change, for instance, at your vertical asymptote. So at -3, you're seeing that, okay, fine, we had this interval where the function was decreasing. On the next interval, it was also decreasing. So what students sometimes will write is an interval that goes from this critical number to the next, and they completely eliminate this vertical asymptote. However, your function's not actually decreasing at a vertical asymptote. It cannot be. The function doesn't exist at the vertical asymptote. How could it possibly be decreasing? You must actually write these, grab my union, as two separate intervals. It is essential. If on your test you combine these into one interval and skip right over the -3, I'm going to take off points. These are two separate intervals. You cannot possibly be decreasing at -3 because your function does not exist at -3. Split those up. So now that we have that, you're looking at what's happening at your critical numbers. You have two critical numbers. I don't care about the vertical asymptote anymore when I start talking about local extrema. Of course, we're not going to have extrema at a vertical asymptote. Like, how can I possibly have a maximum or a minimum if the function doesn't exist there? But what I do want to look at is extrema at our critical numbers. So for our extrema, I'm going to look at what's happening to the sign of the derivative. It is increasing, so I'm going to go up from left to right, up to my first critical number, and decreasing until I hit that vertical asymptote. Then I'm decreasing and increasing. So what you're seeing here is as you go up, you're going to hit the critical number. At the critical number, there's going to be a horizontal tangent line. That's its whole purpose. and then your graph starts to decrease at that point. So this would have to be a local max. I mean, you can see it visually. It's at the top, then you go back down again. So I would say that I have a local max at x equals -3 minus twice the square root of 3. That's your critical number there. So you can't see it. There it is. And then your local max value would just be your function value at this critical number. I'll let you find that. Then you'll have a local min. Notice that you are decreasing on this interval, and then you start to increase. So at the critical number, you hit this point where you have a horizontal tangent line that will represent your local minimum there at the bottom, and it starts to go up again. So you would say you have a local min at x equals -3 plus twice the square root of 3. And then your local min value would be your function value at -3 plus twice the square root of 3. To find the function value, just pop it into your original function f. Okay. The last one I wanted to do was a trig function. So we'll do that one next. And then we'll call it a day. This one's actually a little shorter. I know sometimes we think of trig functions as being something that's going to take a lot longer. That is not the case. So this f of x is sine squared x plus 1. Now I'm going to give you an interval in this case because this function will continue to oscillate for the rest of its life, and you don't have the rest of your life to sit here and find every single critical number because it would take you the rest of your life to do. So we're going to go ahead and look at this on the interval from 0 to 2 pi. The first thing I'm going to do is take the derivative. In order to take the derivative, it will be most beneficial to you to rewrite this by actually applying the square to the entire function, sine x. Okay, take the derivative, use the chain rule, twice the sine of x to the first power, multiply by the derivative of sine x to get cosine x. Now, your critical numbers are going to occur where your derivative is equal to 0. In this case, we don't have to worry about the derivative not existing because you don't have any values in the denominator here. So f prime of x equals 0. I already did that, so let's just go ahead and solve this equation. That's going to happen when sine x equals 0 and when cos x equals 0. Just use the 0 factor property here and take each factor and set it equal to 0. All right, you got to know your trig function values, team. Remember that the sine of x is represented by the y coordinate. So in this case, for instance, you're looking at the point 1, 0. Over here, you're looking at the point -1, 0, 0, 1, 0, -1. If the y coordinate represents sine, well, your y coordinate is going to be 0 over here when we're talking about the value, the angle 0, and then also over here at pi. Forget we have pi, pi over 2, 3 pi over 2. So we have x equals 0 and x equals pi. The cosine of x is going to be 0 anytime we're on these north and south poles. So pi over 2 and 3 pi over 2. And you now have, oh, you know what though? I cut you off here at 0. So actually, let's not include 0. Lucky for you, that's one value you don't have to worry about because it's an endpoint. You can't possibly have a local extreme value at an endpoint. So don't include 0. We'll just start at pi over 2, and then we'll have pi and 3 pi over 2. When we set up our intervals, I want you to be very careful here not to take your intervals starting at negative infinity. Start them where I started you at 0 and end them at 2 pi, because you don't want to end up picking a test value that's outside of the actual interval that you're working with, because you might pick one that's further on down the line where we haven't looked at the critical numbers yet. And then you could end up getting a wrong answer, which nobody wants. So we're going to go from 0 to pi over 2, from pi over 2 to pi, and then from pi to 3 pi over 2. Inside here, we're going to pick test points, and then we're going to evaluate the derivative at the test points. I occasionally have students come up with really bizarre test points. Pick something that's a basic angle that you know something about. Yes, technically you could enter into your calculator pi over 2 and get approximately 1.57 and then pick a test point at like 1. I guess it works, but if I were you, I would just pick an angle. If you really don't know your trig that well, just fine, pick a number. It doesn't really matter. But if I were you, I'd pick a special angle, like pi over 4. So pi over 4 is between 0 and pi over 2. I'd pick that because I know something about pi over 4. Between pi over 2 and pi, I would probably do 3 pi over 4. And then between pi and 3 pi over 2, I would probably do 5 pi over 4. That's just me. You pick the test points that you want to use. Those are the ones that I would use. And I just happen to use multiples of pi over 4. You could use pi over 6, pi over 3, whatever you want to do there. Just pick a special angle. All right, now I'm going to take my derivative and evaluate it at the test point. Here's my derivative. But I know that sine and cosine have the same value at pi over 4. They are both going to have the value. I'm actually going to just fill this in so that you can see it. It's root 2 over 2, if that's the way you're used to seeing it. And they're both positive in quadrant 1. So these 2's are going to cancel, and then you have root 2 times root 2, which is just 2, divided by 2, which equals 1. It doesn't even matter what it equals. All you need to know is that it's positive. Now, at 3 pi over 4, the sine is going to be positive, and the cosine is going to be negative, because remember, the cosine is the x value. So the sine is positive, the cosine is negative. I should have made my intervals a little bit bigger here. And you'll get -1. And we know how these trig functions work. They're oscillating. So we're expecting that these are going to change. If they don't, check your work over. 5 pi over 4 is in quadrant 3. Sine and cosine are both negative. You're going to get +1. Okay, so now we can make some conclusions about our function. We can say that f is increasing on 0 to pi over 2, and then pi to 3 pi over 2, and f is decreasing on pi over 2 to pi. Now, if you would like a visual to talk about extrema, up, down, so your function's increasing on this interval, and then it gets to this critical number at pi over 2, and it starts to decrease. So we would say that pi over 2 would be a local maximum. And then a local minimum would occur at our other critical number. Oh, you guys, I totally forgot to take this up to 2 pi. Sorry, you know, I was very distracted because my husband has this wedding to go to, and he's in here like trying to get ready, and I'm trying to teach, and it's really awkward. Oh, I wish I could go back to the classroom so bad. It's just crazy. Okay. let's finish this last interval here. 7 pi over 4 is in quadrant 4. In quadrant 4, sine's negative, cosine's positive. So sine is negative, cosine is positive. You get a negative here. So don't want to forget what's happening there. So f is also going to be decreasing on the interval from 3 pi over 2 to 2 pi. All right, now we have a local minimum value at pi, because notice that at pi, our function was decreasing and then started to increase again. And then we have another local max at 3 pi over 2, because your function was increasing and it got to the top and then it went back down again. So 3 pi over 2. If you're looking for the values, we would say that we have a local max value. One of them would be at f of pi over 2 and f of 3 pi over 2. You know what? Let's just find the values real quick. So those will be your local max values, and then the local min value. We're just going to have one local min is at pi. Okay, so at pi over 2, I'm going back to our original function here, f. The value is actually on the graph, so we're looking at f, sine squared x plus 1. So let's see. Sine pi over 2 squared plus 1. Sine pi over 2 is 1. Square it, you still get 1. So your value is 2. And then the sine of 3 pi over 2 is negative 1. But when you square negative 1, you still get 1. 1 plus 1 is 2. The sine of pi is 0. Square it and you still get 0. Add 1 and you get 1. And it makes sense that your max values would be the same, because, you know, we just have this oscillating trig function. So it's going to hit the value, it's going to go back down, it's going to hit the max again, hit the min again. And if we took this interval out even further past 2 pi, you'd see that behavior continue. Okay. That's what I had to say about 4.3. And honestly, that's like the first half of 4.4 right there. It's just talking about using the first derivative test, which seems super, like when you hear it being said, it seems like it's really complex. But I feel like it's pretty straightforward to use the first derivative test, because all you're doing is just kind of following the signs of what happens here and just saying, okay, well, if we change from positive to negative, then it must be the case that our critical number is represents the location of a local max. If it goes from negative to positive, then our critical number is a local min, so on and so forth. Okay, so that was what I had to say about that. Next time, we are going to talk about concavity. So I don't have anything else to say about increasing or decreasing right now. I'm not going to say much more about it on Monday. On Monday, we're going to talk about whether or not your function is, we'll talk about whether your function is concave up or concave down. And we're going to use a test for concavity using a second derivative. And then we're going to talk about inflection points, which for concavity are kind of like critical points. And I'll give you some more functions, some more practice with different types of functions, some natural log functions. We'll put it all together. We'll even have a second derivative test for local extrema. And then we'll sort of put it all together in one example. And then we'll start in 4.6, graphing functions. I don't know if we're actually going to get to 4.6 Monday. I'm guessing I'm going to have time to give you like one example, but they're pretty long examples in 4.6. So we're going to spend quite a bit of time on 4.6 next week. Okay, so that's kind of my plan. Monday 4.4, maybe one example from 4.6. And then Wednesday, 4-6, like the whole time. Thursday, I want to talk about optimization from 4-7. And then your asynchronous work next weekend will be just more 4-6. And then we'll work on 4-8 the next week. And then your test will be Monday the 12th on 4-2, 4-3, 4-4, 4-6, 4-7. 4-2, 4-3, 4-4, 4-6, so 5 sections. Okay. Email me if you have any questions. I'm going to put up some homework so that you can get started. I'm going to have to figure out how to incorporate some of this first derivative stuff into your homework. The way they split this up drives me nuts. But such is life. You guys have a good weekend, all right? And we'll have a quiz on Monday covering 4-2 and 4-3. I won't ask you any 4-4, but it all just comes from the same place. Okay. All right. That is all. Have a wonderful weekend.